This next principle I've called the energy mass dissipation principle of stellar evolution. A simple principle of stellar evolution is written to account for the rate of dissipation of energy and mass during stellar evolution according to stellar metamorphosis. According to stellar metamorphosis, stars are non-equilibrium dissipative structures, meaning they're not in thermodynamic equilibrium. If they were, they'd be really cold. Clearly they're not. They're really, really hot. They cool and become what are called planets or exoplanets by astronomers. They're actually all astrons, thanks to Michael Z. Young astrons can be called stars, and old ones can be called planets or exoplanets. You can still use those terms, but you have to understand that they're not different. They're highly evolved stars. That's what an exoplanet is. They are the same objects, only in different stages to their evolution. To account for all the energy loss, so that theory can be further clarified, the energy mass dissipation principle is as follows. I have written here, the rate at which astrons, which are stars, exoplanets, planets, lose energy and mass decreases as they evolve. All this means is you have young astrons losing more heat and mass than older ones, because the older ones are less thermodynamically active. The Earth is a lot less active than the Sun. They have aged considerably and cooled down. Put in even more simple terms, rocks do not shine like plasma. This could also lead to more discovery concerning the causes of gravitation, as the oldest stars are comprised of rocks and minerals and are less gravitationally attractive than stars comprised of gas and plasma. There is a reason why we will never find a rocky world the diameter of the Sun, and it is not what mainstream astronomers think either. They don't even know what they're standing on. That's a fact. Mainstream astronomers, they still don't understand stellar evolution or planet formation at all, because they have separated the two in their minds. There's no hope for them. We have to completely go around them now. We can't rely on them anymore for any reasonable interpretation of the stars or planets or anything of that nature. But anyways, what this really means is that if you have a big, hot, bright star, okay, it's going to remain bright and hot for a very short amount of time. I'll just put 10 million years right here, okay? But then it reaches this level, and it will remain hot and bright and shining at that level for maybe 30 million years, okay? And then once it reaches this level, it'll stay at that for 60 million years. And once it reaches that level, it'll stay hot and bright, or stay hot for, at that level, about 200 million years. And then it just keeps on going. Eventually you get to the point to where it's like a gas ball, and it's completely trapped a lot of the heat. And it ages very, 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 very slowly. So, 1.5 to 2 billion years plus could be at this stage. And then once the crust completely solidifies over it and there's still leftover magma inside, it's like, really, really small, it ages even further. This isn't, perfect. This is just to let you guys know that it would be like 2 to 10 billion years. And then it would keep on going. So basically you have a really hot, bright star, and it takes longer per the amount of time to evolve, per amount of time that it evolves in. So the rate at which it loses its mass and energy slows down. So hot, bright stars stay hot and bright for short amounts of time, and very, very cool stars that have internal layers of heat stay hot for incredibly long amounts of time, much, much longer than these stars. So once you get down the line, the rocky worlds get older and older and older as you look at them. So you could have an Earth-sized planet the same size as another one, but they could be 10 million years older than one another, or 30 million years older than one another. It would be really hard to tell the difference between the two. Because they're so old. But if you have young stars, you can tell there's a bigger gap there. You can tell a lot easier how much older one is than the other when you have a high rate of energy loss happening earlier during the star's evolutionary path. But yeah, basically that's it. Today is March 13th, 2016.